Hello everyone, this is ASCIIchart.com. I'm just zoomed in on the content of the page. Make that a little bit larger so it fills the window a little bit better. So what this is showing is the numerical representation on the left side of the column, and on the right side of the column the glyph or character if it's printable, or the command code that's being sent if it's not printable, is in the right-hand column. So as we can see, the first 31 characters are non-printing characters. So decimal 7 causes the beep sound that your computer makes. The decimal 8 is backspace. Decimal 9 is a horizontal tab. Decimal 11 is a vertical tab. So you need to remember this code is old. When this code was created, we didn't have screens to display computer output. Computers were connected to teletypes or to printers, and so it was necessary to be able to control horizontal and vertical positioning on paper. That's why we have codes like this: 13, carriage return the carriage to the left-hand side of the printer, and decimal 10, line feed, advance the page one line up. These two characters, carriage return and line feed, still factor in because Windows systems use this, both carriage return and line feed, together. So they're two characters that get put into your text files every time you use a \n. Anyway, we come over here, decimal 32, space. So a character that we can't see has to have a numerical representation. Then we have some punctuation, and here we are. The glyphs for numbers 0 through 9 have decimal values 48 through 57. Then we squeeze some more punctuation in, and you'll notice that uppercase A begins at decimal 65, and it's alphabetical order until we get to uppercase Z at 90. A little more punctuation, and then lowercase a at 97, up through lowercase z at 122, and then a little more punctuation. Now this takes us up to 7 bits. These are the characters we use in the United States. They quickly realized, the folks who were standardizing computer encoding realized that, well, we have one more bit for a byte, so that gives us another 128 characters, and so we end up with extended ASCII, which is not represented on this chart. But that includes things like things with diacriticals, the nye for Spanish, so the n with a tilde over it, or the accent grave for French, where the a with a backwards facing apostrophe over the top of it, umlauts for German, and some other special characters. That's still not enough characters to represent the entire breadth of languages in the world. In fact, if you only have 256 glyphs, you quickly run out of those. You can't do Cyrillic, you can't do Hebrew, you can't do Chinese or Japanese and any of its variations, you can't do any of the Arabic languages. So what ended up happening is that instead of using 1 byte per character, we now use 2 bytes per character in an encoding system known as Unicode. Just keep in mind that you may inherit an old system that assumed that characters were only 1 byte long, because I did in my programming career. We had a project that was international, but some of the developers that were on it used 1 byte for character in strings, and we had to rewrite all of the low-level string handling, and this was a Java system. So it was also like different libraries were talking to each other in different ways. It was an interesting little headache. Anyway, this is why when I said that the character 6 is different than the number 6. So a numerical value of 6 is a certain binary pattern inside of a variable. But if we know that we need to treat that pattern as a character, then if we would need to make sure that the pattern is a 54 to us if we interpret it, because to the computer that would output a symbol that we would read as 6. If the internal pattern was actually the pattern for the value of 6, it would be over here in one of our non-printing characters that would send a code for acknowledgement. So keep in mind that, and I'm going to say this again and again through the semester, everything we do with computers ultimately is a lie. And what I mean by that is that there are different levels of abstraction that get layered on top of the underlying electronics. And as we get farther and farther away from having to work with that low level, it's easy to forget that these layers exist. Most users don't need to worry about that, but you as programmers need to dig into it, and you need to understand it, because it'll help you understand why you get some weird error messages from time to time. Okay, I hope this was informative.